Hello everyone, this is Saksham Jain and I welcome you all to the Future Camp. So in this video, we will be covering multivariable linear regression as well as polynomial linear regression. This video is the advanced portion of our previous video that was of one-dimensional linear regression. So in this video, we will be dealing with all the mathematics that is behind multivariable linear regression. We will code our own multivariable linear regression code as well as use Scikit-Learn to implement that. And at last, we will code our own polynomial linear regression code. So all the datasets mentioned, or I can say all the dataset used in the code, you can find them in the description below. And if you want to stream this whole video in Hindi, then the link for the same as well as the link for the Hindi channel can be found in the description. So do check them out. So without wasting any time, let's get started. So in the last video, we had denoted our target variable as capital Y and our predicted variable, that is the value that has to be predicted by our model, as Y cap, or we can say Y hat. And our target value meant that it was the actual value of our feature, or I should say of our independent variable. But here, since we will be dealing with a little complex calculation in our mathematics stage, so I will denote my target variable as capital T and my prediction as Y. In the last video, that is in the case of one-dimensional linear regression, our aim was to minimize our error function, and our error function was target value minus of predicted value whole square summation. That was our major aim in the previous video. That was to minimize this error function. Our error function was denoted by E. We can also call our error function as cost function, and since we are calling it as cost function, I can denote that by C. Basically, cost function and error function are same things. They are two terms which literally mean the same thing. But when we hear the term cost or error, the first thing that comes to our mind is we have to minimize these things. We always try to minimize the error, we always try to minimize our cost. So whenever we use the term error or cost, our basic aim is to minimize. But when we are not certain, when we are not sure that whether we have to minimize or we have to find the maxima, then we use a specific term called objective function, and it is denoted by letter capital J. And in this video and in this multivariable linear regression calculation, I will be using this objective function. Now comes our weights, also known as parameters. So our weights or parameters are denoted by capital letter W. So weights basically mean how much importance I have to give to this particular feature. For example, I'm building a model, or for example, I have to predict what is going to be the price of a house. So I have to take many cases. I have to consider many cases, like what is the location of the house, what is the total area on which the house is spread, and how many rooms are present in the house. So there are many features, many things that I have to look upon. But there are some particular features that play a major role in calculating or in predicting the price of the house. For example, sometimes location play a major factor in determining the price of the house. For example, if someone is living in a big city and other person is living in a small city, comparatively smaller city or town, then whatever might be the area of the house, since the first person is living in a big city, therefore the prices of the house automatically spikes up. So in some features, some features are important and some features are less important, and their importance is measured by the weights. So we multiply each feature by its corresponding weight. So each feature has a corresponding weight. In 1D linear regression, when I had one independent variable x, or I can say when I had one x, I had to find one output y. When I had n number of x, that is, I had a column full of independent variables, I had to find n number of y. But in multivariable linear regression, when I have to find one output, I have to give a larger number of features. For example, I have to feed d number of features. Here in D, this can be x1 feature, this can be x2 feature, this can be x3 feature, this can be x4 feature, and so on. This can be xd feature, and on the basis of these features, on the basis of D and on the basis of these D features, I have to find y, my target or my actual value. And this was a case of one sample. If I am taking n samples, we don't rely on just one sample. We have to take multiple samples in order to forecast something or predict something. We have to feed our machine learning model n number of features so that it can train itself. So if I have n features, so if we can visualize this in a way of a matrix or a figure, I can say that here the length is n and the width is d. So there are d features, and in total there are n samples, and correspondingly I will get n number of outputs, and this length is 1 corresponding to each sample. So these were the basic things that you should be knowing about without starting a mathematical concept. So let's start with the mathematics part. In 1D linear regression, we were finding y cap, which was equal to ax plus b. But here, since I am dealing with multivariable linear regression, I will write it as wx plus b. And since there are d number of features, that is, there are more than one number of features, I am going to write this equation as w1 x1 plus w2 x2 plus, and this will go so on till wd xd, because there are d features plus the bias term. Here x1 is first feature, x2 is second feature, and so on, and xd is the dth feature, and correspondingly each feature has its own weight. Now I am going to write this equation as w0 plus w1 x1 plus w2 x2 so on till wd xt. Here I have replaced my b term with w0. I can write, since b is a variable, I can write it as b, or I can write it as c, or I can write it as d, or I can write it as e. It's my choice. So I have written b as w0 so that now this equation looks a little more uniform. Now what I'm going to do is I'm going to multiply w0 with x0, and then I'm going to write the rest of the thing same as before. So until wd xt. Here the value of x0 is 1. So I have written x0 whose value is 1, so that this equation looks uniform, and I can write this term similar to this series. After this, what I'm going to do is, in case of one sample, if I'm dealing with one sample, I can write it as y cap is equal to wt xi, where w is a matrix of, or I can say an array of d features. But in case of n sample, this equation will look like, I'm no longer going to write this as cap. I will write it as just in a form of vector. I will denote this by arrow underneath underneath y arrow is equal to xw. Here the dimensionality of x is n number of samples multiplied by d features, and dimensionality of w is 1 cross d. Here you can see that dimensionality of w is, since there is one row, I will write it as 1, and there are d features, so I am going to write it as d. D features. But since there is a transpose here, what I am going to do is I am going to rewrite this equation as d cross 1, because w is having a transpose. Therefore I am no longer going to write the dimensionality of w as 1 cross d. I am going to change it as d cross 1, so that matrix multiplication is possible. Matrix multiplication is always possible only when these two values are equal. So now I will find my objective function, which is equal to summation of target minus of predicted value whole square, and I can write this further as t minus y transpose multiplied by t minus y, where t is my n cross 1 matrix of target values and y is my n cross 1 matrix of predicted values. Now I will open up these brackets and my objective function will look like t transpose t minus of t transpose of y minus of y transpose of t plus of y transpose of y. Now I am going to substitute the value of y with xw. So now my equation looks like t transpose t minus of t transpose of xw minus of xw transpose of transpose multiplied by t plus xw whole transpose multiplied by xw. So in 1D linear regression, what we had done was we had to find the values of a as well as b, and to find that we differentiated our error term with respect to a as well as with respect to b, so that I can get two equations, and after solving those two equations and I will get the value of a and b, because it was like a form of linear equation in two variables. But here, since there are no a and b, and here in place of a and b I have written w, so what I'm going to do is basically w is my matrix of a d cross 1 dimensionality. So what I'm going to do is I'm going to differentiate this whole equation with respect to w, so that finally after differentiating it I will get the value as minus 2 x transpose t plus of 2 multiplied by x transpose xw. And since after differentiating I have to put the whole equation equal to 0 in order to find the maxima or minima. What I'm going to get is 2xt xw is equal to 2x transpose t. The 2's will get cancelled, and now I have to shift, or now I have to transpose this term over here. But since these are not any random numbers, these are matrix. I cannot divide any matrix with another matrix. What I have to do is I have to write this as a form of w is equal to x dx inverse of x t t. I cannot divide this term with this term. What I have to do is I have to write this whole term as inverse multiplied by this term. So now my w is going to look like this, and now I have to find this value. So now let's start by coding a multivariable linear regression code. So first you have to import your NumPy, Matplotlib as well as pandas, and since we will be visualizing our data in 3-dimensional, because this is not 1-dimensional linear regression, this is multivariable, so there is definitely going to be 3D axis and sometimes more axis, but we will be using 3D axis to visualize our data. So we will import our axis 3D, and after that we will type bang-it, and we will import our dataset by typing the URL. You can find this URL from the description below, or if you want to check this URL from GitHub, then you can find the same by searching the file name which is data_2d. So after importing your dataset by using bang wget and typing the whole URL, you can find your dataset by clicking on the button on the left side here, and you can see your dataset here. Here you can see my dataset data_2d.csv. So what you have to do is you have to click these 3 dots, and after that you have to click on copy path. So once you have copied your path, you are good to go. So after that, what you have to do is you have to create 2 arrays x and y. And after that you have to open our dataset. So you have to write for line in open. So what is line variable? Line variable will iterate through each of the rows present in the dataset, and after that you have to open the dataset. For the dataset you have to paste the address that you have copied earlier, so which is content data_2d.csv. After that you have to create 3 variables which are x1, x2 and y. So since this is a multivariable linear regression, therefore there are definitely going to be more columns. So this is my x1 column, these whole values, this is my x2 and this is my y. And after that, you have to, since this is a CSV file, so all the data is separated by a comma. So you have to write x1 comma x2 comma y is equal to line dot split comma. So this will split my data set wherever comma is coming. And after that, what you have to do is you have to append the dataset in the x arrays as well as y arrays. So you have to remember to use float here. And why you have to do so? It is because when you will split the dataset here, the values that will be stored in x1, x2 and y are of string data type. So you don't want string data type because we are dealing because we will be predicting some numbers, so we want to insert some numbers to our model. So we will convert our data set to float type, and you have to remember to add 1 here. Why 1? Because you must be, because in the mathematics part, what we had done was we first wrote our equation y cap is equal to b plus x1 w1 plus x2 w2, and after that we had written w0 plus w1 x1 plus x2 w2, and after that we had written w0 x0 plus w1 x1 and so on. And w0 and x0 represents 1, so it is like adding 1 to our whole data set. So you have to add you have to append additional column with 1 value, and you have to do the same thing, not same thing, you have to append the y column, that is your actual value, your target, to your y array. After doing this, you have to convert your whole dataset, your x and y, to numpy arrays because they are easy to deal with. So once you have done that, you can check the shape of your x. So the shape of my x is coming to be 200,3, which is perfectly fine. So now you can check your data set x. So my x is having 3 columns, where the first column is the data set. The first column and second column are the same as what we had copied from our data set, and the third column is something that we have added on our own, that is 1, that is a weighted term. And once you have done this, what you have to do is you have to plot a data set so that you can easily visualize how your data set will be looking. So once you will do that, once you will type this code, so you can see my data set like this. So this is a 3D plot, and my data set has been scattered here and there, and it is easy to visualize because of 3D, because it is a 3D plot. Now what you have to do is you have to use the equation that we had derived earlier on your whiteboard. So in our whiteboard, at last, what we had done was we had derived our w is equal to x transpose multiplied by x whole inverse multiplied by x transpose multiplied by t, where t was our target variable, x were our features, and so on. So we have derived this part earlier. So now what you have to do is you have to write w is equal to, w is our weight variable, is equal to np.lineage.solve. So what will solve do is, once you have written solve, then you don't have to write this inverse term. You have to just feed this thing. You just have to pass these two in the argument, that is x transpose x and x transpose t, that is x dot x and x dot t, and you don't have to write -1 because solve function will take care of that. So once you have done that, you have to basically write w is equal to np.lineage.solve and np.x.t comma x and np.x.t comma y. So you don't have to use inverse because we have already written solve. You just have to write these terms here, x transpose x, basically x transpose dot x and x transpose t. You can see that here, and our basically t is our target, and here I have denoted my target as y. After that, you have to write your y hat, your predicted y hat, and which is going to be np dot dot, and it is going to be the dot product between our features, that is our x matrix, and our weight matrix w. Once you have done that, you are good to go. You just have to calculate your r square so that you know how good your model is. So for that, you have to just write the same code which we had done in our earlier video. That was basically our r square code is nothing but 1 minus sum of square of residual divided by sum of square of total. So here this is my sum of square of residual, this is my sum of square of total, and this is my r2, and I've calculated my r2. If I print the value of my r2, it is going to be 0.998. So please remember this value because this will help us in comparing how good our model is in comparison to Scikit Learn. So once you have done that, let us predict a value on of predict some value on our own. So basically, let me pass this dataset as my test dataset. So this is the dataset. I'm passing 31 as my feature 1, 54 as my feature 2, and 1 is my is my bias term. It is the one column that we had earlier added. And once I run this, what I have to do is I can check my shape. So it is perfectly coming to be 3 comma something, 3 comma nothing. So I will reshape it because I want some specified correct shape in order to correctly implement my code. So I will reshape it and put -1 comma 3. So what will it do is it will make sure that my array or my matrix or my data set now has 3 columns and required number of rows. Basically, -1 means I'm not specifying how many rows are needed. My computer or my compiler will take care of that. And 3 basically means that it should have 3 columns. So once you have done that, what I can do is I can check my shape. So my shape is perfectly fine. Now what I have to do is I have to predict my value. For that, you must be remembering that my y hat is equal to my predicted value. So my y hat is equal to np dot x comma w. So basically my y hat is nothing but the dot product between my features and my weight matrix. So I have to take the dot product of my features and my weight. So weight has been calculated here. So only thing that I need to pass is my feature matrix, and here my feature matrix is x underscore test. So I have to pass np dot x underscore test. This is my feature matrix, and my weight has been calculated earlier. So once I run this, I can predict the value. So when my feature is 31, first feature is 31, second feature is 54, then my value is coming to be 224.3505. Now let us implement this whole model with the help of Scikit Learn. So in Scikit Learn, what you have to do is you have to just import pandas, numpy as well as sklearn. I'm doing the same things that I have done earlier. I will use the bang get and pass my URL, and after that I will create my x and y arrays, and after that I will split my dataset in my x1, x2 and y, so that I can split my dataset in my feature as well as my predicted value as well as my target variable. And after that I have to convert my dataset into numpy arrays, because numpy arrays are easy to deal with. Now I have to load my linear regression model, and I will name it as LR, and I will fit the values. I will pass on the values of my feature matrix and my target matrix or my target column. So I will write lr.fit x comma y, and after that I have to predict my model. So I will write y underscore predict. This is my prediction variable. This will predict the value once I pass my x, and I have to write lr.predict x. So basically now my model will try to predict the values of my y matrix when I will pass the features. So once I've done that, I will check my predict matrix, which is coming to be array, and where the first values look like 318.33 and 404. And if I compared it with my target values, see, this is my actual value. This is the value that my model has predicted, and my target values were those outputs that I have given. These are the real values. These are my actual targets, actual prediction that should come, and y underscore predict is the value that my model is predicting. So you can compare it here. My target is 320 and below it is 404, and my predict is coming to be 318 and 404. So yeah, slightly different, slight difference is present there, but yeah, my model is working absolutely fine. So that was all for multivariable linear regression. And now let us check our polynomial linear regression code. So my polynomial linear regression code will work exactly same as my multivariable linear regression one. So I have to import my numpy, I have to import pandas, I have to import my matplotlib. After that, what I have to do is I have to gather my data. So my data set can be gathered by just typing my bang get, and after that I have to specify my URL, and after that you have to follow the same steps. So you can find the link for the data set in the description below, or you can visit my GitHub profile and find the data set with the name data_poly.csv. So this is my data set and I have imported it. So I will here follow the exact same steps that I have followed earlier for my multivariable linear regression. So I have to create my X array, my Y array. I will open the file just like the way. So since I have imported my polynomial linear regression file dataset, so you can see my dataset to be here. Data_poly is here, and I will copy my address here and I will paste it when I'm opening. So I will write for line in open, I will pass the address here, and after that I have to write x comma y is equal to line dot split. So you must remember one thing, either you can, sometimes you have to pass the complete address of the file where it is located, and sometimes you just have to pass the name of the file. Since it is located here only, so just the name will also work sufficiently. But if this file is located in some other further folder, then for example you have uploaded multiple folders, then you have to specify the perfect address. Otherwise just by passing the local name will also work. So I have to specify my x variable and my y variable, that is my independent and my y, and I will append 1 comma x square. Why I'm putting x square? Because polynomial linear regression is basically deals with these kinds of curves. So basically in linear regression my curves is this, and in multivariable linear regression, if it is in 3D axis, it will also be a straight line. But in polynomial linear regression my curves are like this because my graphs are x square, x cube, basically non-linear terms. So I will do this, I will append these values in my x array and my y array, and after that I have to convert these array into my numpy array. After that I will plot. So for plotting I will write plt.scatter and I will plot my data set. So my data set looks like this. So what I have to do is I have to first calculate my weight, and for weight calculation I will use the exact same code that I have used for multivariable linear regression. I will write w is equal to np.lenarch.solve np. and x.transpose, which means x transpose, comma x, and dot product of x transpose and my target values. And once I have run that, what I have to do is I have to check how good my model is. For that I will write the exact same code for my R square, and after I have done that, you can see my accuracy to be 0.991 something, which is absolutely amazing. So which means since it is close to 1, it means that my model is working pretty much fine. Now what you can do is, as a homework, you can implement the same code in Scikit Learn, and remember you have to make no changes. Your code is going to work exactly as the way it was working for multivariable linear regression. So you can type the same code for polynomial linear regression. So that was all for today, guys. We have covered all the mathematics behind multivariable linear regression. We have implemented our multivariable linear regression code, and in Scikit Learn as well as without Scikit Learn, and we have also implemented our polynomial linear regression code. In the next video, we will be discussing about overfitting, underfitting, as well as L1 and L2 regularization, that are my ridge and lasso regression. So let's meet in the next video. Until then, bye bye.